Hey guys, I wanted to make a little bit of a tutorial because I was having a really tough time with photosynthesis and light reactions and CAM and C4 and all of that. And I was having a really tough time finding a YouTube video that had everything. So I decided I'm gonna make it. So this is what this is. I hope you like it. So this is going to be, we're gonna start off with light dependent reactions, photosystem 1, well 2 and 1 because we're special and we have to start off with photosystem 2 and then go into photosystem 1. We're gonna hit the Calvin cycle, C4, C3, CAM, and then photorespirations. So over here we have our sun. He's very small because he's far, far away, and he's going to be emitting some protons, so that's coming down. They're going to hit the leaf, so we're going to expand it a little bit further. This is our plant cell. Here's our chloroplast, and that's what it looks like, a little bit more expanded out. We have our grana, these are those pancake type things, and that's for, we have a whole bunch of those pancake types all together. This is our granum, that's just one. So the way I think of that, it's like granum 1. I don't know if that helps me. So that's what's happening here. That's what this is. So this is just blown up more. Hey guys, we're gonna start off with light reactions, but I wanted to show you first a little bit of what photosystem 2 and photosystem 1 looks like if it's blown up a little bit. This is our thylakoid membrane over here. You see photosystem 2 and photosystem 1. Now I've drawn this over here and we've expanded it out. I'm gonna go through this now. Okay, so over here we have photosystem 2 and photosystem 1. 2 is gonna come before 1. What's happening is we have the sun up here. It's going to emit these photons and they're going to hit the antenna molecule here. They're going to go in a wave in one direction. The way I like to think about it is like at a baseball game when there's that wave that everybody does. That's exactly what's happening here, where the electrons are being transferred, the energy is being transferred. So we have that happening in one direction. Meanwhile, we also have water that's being split up. It's got oxygen, we have hydrogen, and we have an electron. So that's going to go up here. Together we have it's going to hit this pigment molecule and be absorbed by it. It's called the chlorophyll A pair, the P680, which is PS2 electron acceptor. So from there, that wave is gonna happen. A good way to think about it is over here, where this is gonna be ground state, this is excited state. So we're gonna be moving from this to this. So that's what's happening here. So we're gonna be moving from ground state up to the excited state, and up into the reaction center. So from here, this is the electron transport chain. Still, we have this electron transfer that's happening and ends up here in photosystem 2. We're still going to get photons from the sun in PS1. It's very similar to PS2, just we have a different reaction center. And our pigment molecule is a little bit different as well. So from here, same thing happens. We have the antenna molecule and that wave is still happening. We end up here from ground state and we're gonna go up here to excited state. And then we're gonna continue. But I just wanted to go into a little bit more detail about photosystem 2 and photosystem 1. Okay, so now we are back to light reaction land. We have photosystem 2 and we have photosystem 1. This again is the thylakoid membrane, which you can think of, it's inside the chloroplast. This is the outside of the thylakoid membrane, also known as the stroma, and then the inside of the thylakoid membrane, which is the lumen. So what's happening in this one? We went over it a little bit, but I wanted to give you kind of a broader range so you can see everything that's happening. We're going to have some photons coming in here from the sun. They're going to hit these antenna molecules and they're going to be traveling in one direction, which is right up here. That's non-cyclic photophosphorylation, meaning that the electron will move in one direction. There's no funny business. It just goes in one direction. So while that's happening, we have this water molecule here. He's being broken up. We have oxygen, hydrogen, and an electron. The electron will go and meet this area right here. This is the pigment. And from here, we have an electron transfer up into the reaction center. So right here, this is ground level energy. We're moving up. It's exciting to a higher level, an excited level. So from here, we're gonna come back down to the ground level and into photosystem 1. So while that's happening here, we also have the photons coming from the sun. So again, that's the same thing that's happening here with our antenna molecule. It's gonna meet here at this pigment, And from here, we have this excitedness happening. This is the wave that's happening. We're gonna hit this reaction right there, and then we're gonna come back down. So that's the end of that. Now, while this is happening, we have all of these hydrogens here. We have all of this water that's being broken. So what's happening is these hydrogens are gonna move up through this ATP synthase through facilitated diffusion. Diffusion you can think of as a level of high concentration moving to a level of low concentration. Let's look at these hydrogens. We have all of these hydrogens down here. We also have hydrogens up here, but not quite as many. So this is gonna be facilitated diffusion, high level to low level. Also something I just wanted to share with you, the way I remember osmosis, which is different, diffusion is different, it's more of like solutes. Osmosis is, you can think of water, and I don't mean to be religious or anything, but I think like Moses is in there, osmosis, like Moses, and he's parting the sea. I don't know if that helps me, so yeah, I'm not making a stand, I just wanted to share. All right, so we have the ATP synthase, we have the hydrogen going up through this, the ATP synthase is gonna spin, and as a result, we have ATP from ADP, and we have NADPH is producing NADPH. Nope, I'm so sorry, let me go back. It's NADP plus is going to be reduced into NADPH, which is an electron acceptor. All right, one other piece of the puzzle I wanted to go over this. This is photophosphorylation, which is the generation of ATP. So super specialized because it only happens in light reactions. That's photosystem 2 and photosystem 1. Photosystem 2, photosystem 1. All right, so I also wanted to go over oxidation and reduction, which are also in here redox reactions, meaning that electrons are both being lost and gained. Here we have two reactions, or two equations, I should say. We have photosynthesis here, and we have aerobic respiration here, and you can see both of those pathways happening. So here we have, this is being reduced, so we're accepting that electron, and here, this is being oxidized. We are losing an electron. Same thing over here, this is being oxidized into this, we lost the electron, and over here, we're reducing, over here, we're accepting an electron. So these are redox reactions. All right, now we get to move on into the Calvin cycle. Now you might also see it known as the dark reaction or the light independent reaction. It's all the same thing, it's all the Calvin cycle, so don't worry about that. But what's cool is that we get to use what we just made over there in the light dependent reactions, we get to use it over here. So I'll go through the outputs and the inputs and all of that, but just know that these can happen simultaneously. And something else to keep in mind, we're still in the stroma. We didn't move. So there's a lot of locations, there's a lot of things to keep in mind. So just kind of keep, thinking about that. So we're gonna start off, this is actually a C3 pathway, meaning that this is what most plants do. Eventually, on a different whiteboard, we're gonna go into C4, we're gonna go into CAM, and these are all adaptations of the Calvin cycle. So it's just, this is kind of what the plant wants to do. It's got everything, it's got it all figured out. When it has to move to those other things, it's because it's really not the best environment for them. They don't have a lot of water, it might be really hot, so those are adaptations. So we're gonna stay here. This is really where the plant wants to be. So just keep that in mind. These are good conditions. So this is the carbon fixing cycle, basically making the carbon good for the whole Calvin cycle. Later, we're gonna talk about if this is lost, which this is a big deal because we have a whole phase dedicated to that, or a whole stage, I should say. So the next stage is reduction. That's this whole part. So we move from 6,3-PGA into 6G3P. Hopefully you're not dyslexic like me. I need to really focus on the letters. So just be aware, we're very similar. We still have 6 of each here. And this is needed for glucose. So now we're going to move on into this section. But before that, we have one output. We have one G3P, which is what we need for glucose. Yay! This is what we want. This is, this whole pathway. We get a couple of things out of it, but we're really looking for ATP. Okay, so then we're gonna move on. Something else to be aware of is we have 6, we have 1. Well, what do we do with the other 5? Well, now we're in regeneration. We're also known as the carbohydrate shuffle. So we wanna reuse that. We're gonna use 3 ATP into 3 ADP, and we're gonna get 3 RUBP. So this is the regeneration, stage 3, and now we're gonna do it all again. So here is the reaction for the Calvin cycle. We can see the inputs on the top and the outputs on the bottom. So we have 3 carbon dioxide plus 9 ATP plus 6 NADPH turns into, now we're at the output section, G3P, 9 ADP plus 6 NADP positive, plus P, some inorganic matter. But what's cool about this is you can look down. So we have 9 ATP turns into 9 ADP, because we used it. And then again, 6 NADPH into 6 NADP positive. So, and then this is what we really want. This is, there it is, yay. So, cool beans, moving on. All right, we're moving on to photorespiration. Here we go. So this one's not as fun. The cell doesn't really like doing it. Honestly, it happens by accident. So Rubisco will normally catalyze carbon dioxide, but what happens, magic, it's oxygen. And so because of not really great environment, it's too hot, the leaf does not want to lose any more water, so it will close its stomas. So we don't have transpiration, we don't lose any water. The cell's like, oh my God, this is terrifying, this is horrible, let me just put up the gates. And that's great, but what happens is now we have an accumulation of oxygen. Remember from the other slide over there, I know you can't see it, but it's over there, we had the split of water. We had those oxygens floating around. Well, they can't get out now. So they're gonna accumulate. So Rubisco on accident is gonna catalyze oxygen. Now, this is called the salvage pathway because we're trying to salvage the carbon. What's happening, and you'll see this like list of stuff, it's not great. Like this isn't great. It's not as efficient. It eats a lot of energy. We release fixed carbon. So you remember over there from phase 1 where we were making those fixed carbons? Well, now we're gonna lose them. We're losing 3. So, and it yields no sugar or ADP. This is on accident. We're not trying for this. That's why you'll see moving on into here, there are different ways to get around that. So this doesn't happen. All right, so now we're at the C4 pathway. So it's right in the name, C4, we actually have 4 fixed carbon chain. So as opposed to the Calvin cycle, we had 3, it was a 3C or 3 carbon chain. Now we have a 4 carbon chain. So that's the Krantz anatomy, basically making the 4 carbon chain right there. And then the other cool thing about this is now we're in 2 different locations. We're in the mesophyll cell here, where we're making that 4 carbon chain. But then the minute we come down here, we pop off that carbon dioxide in Rubisco, our old pal, we're now in the bundle sheath cell. So these are important. We're changing locations. So we're gonna finish that, we're gonna pop off a sugar, we're gonna finish that, we're gonna come back so that the cycle can continue, so that we don't have this, so that we're not losing stuff, so that we can still work even though it's hot. This is mostly like grasses, things like that, but we're still in this hot climate. So, you know, they've had to create adaptations. Again, it's to make that concentration gradient back to what it was when we were doing the Calvin cycle, so that it's not so much oxygen and that we do have a lot of carbon dioxide so that we can do more, so we can get more glucose, so we can make more of it and not go to this and lose stuff. Okay, so we're at the CAM metabolism, which is really cool. Very different from the C4 pathway. Not much, but again, this is another adaptation, so we don't go through the photorespiration and we don't lose all that carbon fixation. We don't lose all of the CO2 and have an accumulation of oxygen. So the difference with this one is that it's happening nighttime versus daytime. We're still in the same cell. We're still happening in the mesophyll cell, but this pathway, the beginning, and mind you, it's very similar to the C4 pathway, is happening at nighttime. So because it is such a really hot area, it's really hard to survive, the stomata, they have to close during the day so that nothing gets in or out. They don't lose water, they don't lose it through transpiration, and they don't eventually die. So that's why it's all gonna close during the day. So this pathway, it's open, we can receive carbon dioxide, and we can make this happen. So this is happening at nighttime, and it stores it for the next day, when everything's closed, they're still able to produce glucose. They're still able to make this pathway work. Basically, this is cell respiration. We've got glycolysis, Krebs cycle, and the electron transport chain. So I know this looks really crazy, and I probably should have split this up into more slides or more whiteboards, whatever, but you'll see, it'll work. So over here, we're gonna start with glycolysis. Glycolysis is the first step. We have 1, 2, and 3. So yeah, it'll work. So first we have glycolysis, and this has to do with glucose. So we have phosphorylation, where the glucose receives a phosphorus, or a phosphate, I'm sorry. Our next step, B, this is still part of glycolysis. We have the sugar cleavage. So we're splitting of the 6 carbons to now the 3 carbon fragments. And the last step is the pyruvic acid formation. So it's the oxidation of the sugar fragments. So you can see it up here, this kind of it written out. We're missing a couple steps here, but just so you can kind of see what's happening. We have 1 glucose, and it does split into 2. And then we come over here, we lose a carbon dioxide. I'm gonna go over here. And then we have the acetic acid with coenzyme A. We're still in glycolysis. We end up with acetyl-CoA. So something that I do want to mention, we're moving again. We're changing into different locations. This is the mitochondria. Don't you love my beautiful mitochondria? It's so pretty, I know. So we have the mitochondria. We have the cytoplasm on the outside. So all of this, I should go like this. All of this is happening outside. This is happening outside of the mitochondria. So in the cytoplasm. So just so you know where everything is and what's happening, this is aerobic respiration. So these are all those things. The second step is now we're going to go into the Krebs cycle. It's also known as the scary citric acid cycle. Not scary, I just put that name in there because it is. We have to do with FADH. It's really only found in the Krebs cycle, so something cool. And it's an electron carrier. Oh, something else. Glucose, or glycolysis, I should say, you get 2 ATP from it. And I'm gonna make a whole chart at the end, so don't worry. The Krebs cycle, you get 2 ATP. Dude, look at the electron transport chain. Look at that thing fly, man. 34 ATP, 34. It knocks all this out of the water. But the same thing, normally you'll see it, and I saw it in a couple different ways. You'll see the electron transport chain right here. I don't want to throw anybody off, but I was like, let's make it near the membrane, because what's happening, it's kind of like in Photosystem 2 and 1 earlier, where we were using the electron transport chain there, we were making that happen. Same thing's happening, but now it's in the mitochondria. So we're using the mitochondria membrane. So this is a proton pump. Oxygen is going to grab onto electrons plus hydrogen, and look, we're gonna make water. Exciting. We also deal with the ATP synthase, where we were playing with that a little bit earlier, where now, because of the gradient, we're able to produce ATP from ADP. I didn't have enough room on the other slide. So here is the aerobic respiration chemical pathway. Our input is glucose. I know I was gonna test you, but it's late now. But basically it's C6H12O6, which is glucose. The other input we have is oxygen, because this is an aerobic respiration equation. We have 6O2, and then you add enzymes. The output is going to be 6CO2 plus 6H2O plus energy. So we're breaking it up and we're getting a lot of good stuff. Okay, so we've made it all the way to anaerobic respiration. This was common very, very early on when, the gases were still being produced. Basically, the oxygen isn't present. This is the meaning of anaerobic. It produces a lot less usable energy, only two ATP. Kind of embarrassing. I mean, it was trying its best, but the plants are breaking down their glucose into ethanol and then the alcoholic fermentation. Here we do have our inputs, which is C6H12O6, glucose. Our outputs are C2H5OH. We have our carbon dioxide here, and then we also have ATP. So something I did want to speak about as well. So earlier on when we were talking about Photosystem 2 and 1, then we went into the Calvin cycle, it was interesting, and it dawned on me that and I have another little table that goes over it, but basically that whole thing is to produce energy. We're producing glucose, you know, and we're trying to store it. Not that the plant needs everything at that moment, but it's got this whole surplus. Well, what does it do with it? It's going to store it. Everything else that we've done with the glycolysis, the Krebs cycle, and the electron transport chain, all of that is used to break it up and use it for whatever, you know, the cell needs at that point. So that was a really big aha moment for me. Hopefully that can help you guys too. So here's the big scary chart. Don't worry, it's not that scary. We're gonna break it down, but this is basically location. That's a big part of it. The inputs and outputs, and then the net ATP gain. But look at this. Look at that sucker, man, 34, he wins. So we have glycolysis, and that's a 2 ATP gain. Transition, that's like that middle part before we hit the mitochondria. And then we got the Krebs with 2 ATP. The electron transport chain has 34. So I'm just gonna go through them individually. The glycolysis, 2 ATP. The inputs are 1 glucose, 2 ATP, and 2 NAD+. The outputs are 2 pyruvic acid, 4 ATP, and 2 NADH. Our location is in the cytoplasm right before we go into the mitochondria. Next, we have the transition phase. Obviously, we're not really making any ATP at this point. We're just setting it up for the next steps. We have our inputs are 2 pyruvic acid, 2 NAD+. Our outputs are 2 carbon dioxide, 2 NADH, and 2 acetyl-CoA. This is happening in the mitochondria, or we're headed into the mitochondria. We have now the Krebs cycle with the 2. We've got 2 ATP right there. 2 acetyl-CoA, this is the input, 2 ATP, ADP, I'm so sorry, I didn't see diphosphate, plus a P. We have 6 NAD plus and 2 FAD because our outputs is 2 FADH2. 4 carbon dioxide, 2 ATP, 2 NADH, and again the 2 FADH2 happening in the mitochondria. Our last one is the ECT. This is 34, whopping 34. Our inputs are 10 NADH, 2 FADH2. We have 34 ADP plus P and oxygen. Our outputs are 34 ATP. We have water, and we're happening in the mitochondrial membrane, like our beautiful picture over there. All right, guys, we made it to our last table. I did want to compare and contrast photosynthesis versus respiration, just kind of go over some of the key elements, the key differences, and some of the similarities in that, mostly different, but let's go through it. So with photosynthesis, we're going to store energy into sugar molecules. It's like I was saying earlier, where basically that whole thing is to make extra glucose and to store it away, store it for a rainy day. It's like the bank, you know, they're kind of saving their money for when they need it. So that's that whole thing. We're going to be using carbon dioxide and water, and it's going to increase the weight. Think of like a deposit at a savings account. You're putting money in. You're going to make it heavier, if that helps. And we do produce oxygen as well. So now with respiration, we're going to be releasing energy from the sugar molecules. So this is us going into the bank and making a withdrawal. We're going to be using that glucose for whatever we need. If we want to blink our eye or walk, but when it comes to plants, it's, you know, different. Are we going to do meiosis or, you know, whatever the case is? Now we have some sugar, we have some energy we're able to use. We're going to release carbon dioxide and water, the exact opposite of photosynthesis. We're going to decrease the weight. We're taking money out. We're taking energy out. So it's going to weigh less. We're going to utilize oxygen. So that's that aerobic respiration where we're using oxygen. And we're going to make ATP with the energy released from sugar. We're going to make a lot of it. So yeah, that's a little bit about the differences of both of those. Thank you guys so much for watching, if you're still watching. If you need a little bit of a break, please feel free to look at my videos, whichever side that is. But thank you so much. I hope this helps, and I hope you do amazing on your test. And yeah, be safe.